Okay, let's unpack this. Imagine you're running, say, a logistics company. You've got these big decisions, like which warehouses to open. That's a
Huh.
definite yes, no, right? A
Right.
discrete choice.
Right.
But then you also have to figure out how much inventory goes where, how much stuff to ship. And those amounts, well, they could be anything, continuous variables.
Exactly. Or maybe you're scheduling a factory. You've got specific jobs for specific machines that's discrete, assigning this job here. But
It-
then how long each machine runs for? That could
yeah.
be, 4.7 hours, continuous.
You've really hit on the core challenge there. How do you make the absolute best decision when, well, some things have to be whole numbers, or just yes, no, while other parts can be any fraction?
Yeah, exactly. And, standard linear programming, it's great if everything is smooth and continuous, if you can slice it all up.
Right.
But the second you have those either-or choices, those things you can't
Yeah.
divide, well, that's when you need something else, something more powerful.
And that's where mixed integer programming comes in, MILP.
That's the tool. Mixed integer programming or MILP, yeah. At its heart, it's a kind of mathematical optimization. You've got a clear goal like maximize your profit, minimize costs. That's your linear function.
Okay.
And you've got rules, boundaries, budget limits, machine time, staffing rules again, linear constraints. But the key twist, the thing that makes it so potent, is that some of your decisions, your variables, have to be integers, whole numbers.
These integer variables, they're the magic ingredient. They let you model those real-world discrete decisions.
That's it, exactly. They can be binary, just 0 or 1. Perfect for those yes-no questions. Do we launch this product?
Yeah.
0 or 1. Assign this crew to this flight. 0 or 1.
Makes sense.
Or they can be general integers.
Yeah.
Counting things. Number of trucks you need. Number of batches to run. Has to be a whole number.
And that integer requirement, that's what makes it different and harder than pure linear programming.
Fundamentally different. It gives you incredible flexibility to model reality, capture logic, but yeah, it also makes finding that optimal solution a lot more complex computationally.
So, for you, our listener, who follows these optimization topics, our mission here in this deep dive is to really explore this powerful world of MILP. We want to understand its structure, see how it tackles these huge operational challenges, and get a feel for how the software actually finds that guaranteed best answer.
Sounds good.
Let's start right there, nailing down the basics. What exactly is a mixed integer program?
Okay, yeah, let's build on that. So, like we said, linear objective function, minimize cost, maximize profit. Linear constrains the rules of the game. But the defining feature, the absolute key, is that while some variables can be continuous, any real number, others must be integers.
Right, so in pure LP, if you're making chemicals, you could make 150.75 gallons. The solution space is kind of smooth.
Exactly. It's a continuous shape, often a polytope in high dimensions. But for MILP, if you're deciding on production runs, it has to be 10 runs or 11 runs, never 10.3. So the actual feasible solutions, the points you could actually use, aren't that smooth shape anymore. They're just these scattered points inside that shape where the integer variables hit whole numbers.
And those binary O1 variables, you said they're really powerful for modeling choices.
Oh, incredibly. Turn a process on one or off one.
Yeah.
Pick an investment, one or not. They let you build in all sorts of either-or logic that you just can't do easily otherwise.
And then the general integers, just counting things like machines, workers.
Yeah, pallets, batches, anything that comes in whole units. Just forcing that variable to be an integer instead of allowing fractions, it makes the whole problem landscape much lumpier, harder to navigate for a solver.
Right. Finding the best point among scattered dots is harder than finding the highest peak on a smooth hill. Which, okay, brings us to the big question. If it's so much harder computationally, why do companies rely on MILP so heavily? What's the payoff?
That's a great question. And the payoff, why organizations really invest in this, it boils down to a few key things. First, and maybe most important, exactness. Yeah. Unlike heuristics, rules of thumb that give you a good guess, maybe even a great guess, multi-solvers, when they finish properly, can give you a mathematical guarantee that the answer they found is the absolute best possible one, globally optimal.
Wow. Not just a good guess, but provably the best. I can see how, for huge decisions involving millions, that certainty would be incredibly valuable.
Absolutely. Second big advantage, model fidelity. MILP lets you build models that really reflect the messy reality of how things actually work.
Like what?
Things like fixed costs. A cost you only pay if you decide to open a factory. It doesn't matter how much you produce there. Easy to model with a binary variable. Or setup times, minimum batch sizes, complex logical rules, like if you use route 1, you have to use truck type X.
Gotcha. More realistic.
Much more. And third is flexibility. Often once you've got a MILP model, if the business rules change a bit, you can add new constraints or tweak things without having to scrap the whole model and start over. It's a robust framework.
Okay, so it models reality well and it's flexible. Where are we actually seeing this in action? The sources mention quite a few areas.
Oh, it's everywhere, really. A cornerstone for optimizing complex systems. Supply chain and logistics is just massive. Think vehicle routing, figuring out the best sequence of stops for all your trucks. Minimizing distance, hitting delivery windows, respecting truck capacities. That's LOP.
Facility location, too. Where to build warehouses.
Classic MILP problem. Minimize total costs, building costs, shipping costs by choosing the optimal locations from a set of possibilities. The freight transport example is another good one. You've got goods, you've got truck capacity limits.
So discrete choices, how many trucks, and continuous, how much stuff on each.
Exactly. That structure, it pops up all over, often related to something called a knapsack inequality.
Knapsack. Like fitting things into a backpack. Is that the idea?
That's the core idea, yeah. The items are your loads, the knapsack is the truck's capacity, and you're deciding how many whole trucks your integer variable you need to carry everything without exceeding limits. Selecting discrete units for continuous needs within constraints. Fundamental problem.
Okay. And in manufacturing, what about there?
Scheduling is huge. Deciding when to run specific batches on which machines. Assigning jobs to minimize, say, total completion time or machine downtime.
Makes sense. And services too, right? You mentioned scheduling people.
Absolutely. Staff rostering is a major application, especially complex cases like airline crew scheduling. Assigning crews to sequences of flights often involves what's called set partitioning.
Set partitioning.
Yeah, it's about picking valid schedules, sets of flights for a crew, so that every single flight leg gets covered exactly once. The number of possible schedules can be astronomical, so they often use specialized techniques built on MILP ideas to solve those efficiently.
Wow. The sources also mentioned something called industrial symbiosis. Sounds kind of advanced.
It is pretty advanced, but it's a fascinating application. It's about looking at how different industrial plants, maybe a factory, a power plant, a chemical facility, can work together, exchanging energy like waste heat or materials like byproducts or water.
Okay.
MILP helps figure out the optimal network. Should these two plants be connected? If so, how much energy or material should flow between them? It optimizes the whole interconnected system for efficiency or sustainability.
Like that case study with the 5 processes exchanging things.
Precisely that.
Yeah.
Even without knowing every detail inside each process, MILP can find the best way for them to interact, balancing the discrete connection decisions with the continuous flows, finding the best configuration for the whole group.
And what about the bottom line? Are companies actually seeing big benefits from this?
The data suggests they are. Sources mention significant cost reductions, often 10–30% compared to older methods or heuristics. And modern solvers are beasts. They can handle models with like over 1 million variables sometimes.
Billion, wow.
Yeah, and often find solutions very close to optimal within, say, 1% surprisingly fast for many real problems. That kind of performance just wasn't feasible, a couple of decades back.
That's genuinely incredible. Okay, so we've established it's powerful, it's widely used, but it's inherently harder than LP. How do these solvers actually do it? How do they find that guaranteed optimal solution?
Right, this gets us to the core algorithm. The fundamental engine inside most commercial MILP solvers is something called branch and bound, or B&B.
Branch and bound. Okay, it sounds like exploring options and setting limits.
That's a really good intuition, yeah. It's basically a smart, systematic search method. It starts by simplifying things. It solves the LP relaxation.
Meaning
it ignores those difficult integer requirements for a moment. It solves the problem as if all variables could be continuous, just like a standard linear program.
Okay, so if I needed 0 or 1 factory, the LP relaxation might say the best answer is build 0.7 factories.
Yeah. Exactly, or 0.3 trucks or whatever. Solving this LP relaxation is relatively fast, and its optimal answer gives you a bound. It tells you something about the best possible value the true MLP solution could ever achieve.
A bound. Okay.
Yeah.
And if the LP solution just happens to have whole numbers where I need them?
Then great, you might have lucked out and found the optimal integer solution right away.
Right.
But usually you get those fractions like 0.7 factories.
And that's where the branch perk kicks in.
That's it. If the LP relaxation solution isn't integer feasible, you pick one of those variables with a fractional value, say our factory variable at 0.7, and you branch. You create 2 new subproblems.
2?
Yep. In one subproblem, you add a new rule. The factory variable must be less than or equal to 0, the integer below 0.7. In the other subproblem, you add a different rule. The factory variable must be greater than or equal to 1, the integer above zero point 0.7. You're forcing the decision one way or the other.
Ah, so you're splitting the problem at that decision point, creating two distinct paths to explore.
Exactly. You're building a search tree. And for each of these new subproblems, these nodes in the tree, you solve this LP relaxation. That gives you a new bound, specific to that branch of possibilities.
Okay, keep exploring. But where does the bound part really help?
This is where it gets clever. As you're exploring this tree, you might find solutions where all the integer variables actually are integers. You keep track of the best valid integer solution found so far. That's called the incumbent.
The incumbent, the
Yeah.
current best real solution.
Right. Now, when you solve the LP relaxation for a new subproblem down some branch, you get its bound. Let's say you're minimizing cost. If the best possible cost you could ever achieve down that branch, given by the LP bound, is already worse than the cost of your current incumbent.
Then there's no point going further down that path.
Exactly. You can mathematically prove that no solution down that branch can beat the integer solution you've already found. So you fathom that branch, you cut it off, prune it from the tree. You don't need to explore it anymore.
That's smart. So you're not checking every single possibility. You're using the bounds to eliminate huge chunks of the search space.
Precisely. You explore systematically, find good integer solutions, incumbents, to set a high bar, get bounds from the relaxations to see the potential of different branches, and then prune based on those bounds. You repeat this branching and fathoming until no active branches are left.
And that gap people talk about.
Ah, yes, the optimality gap. That's the difference between the best possible objective value suggested by the bounds from the still active nodes in the tree and the value of your current best integer solution, the incumbent. A smaller gap means you're closer to proving your incumbent is truly optimal. Often, solvers stop when the gap is tiny, like 0.1% or something.
Okay, branch and bound is the core logic. But I guess for big, messy, real-world problems, you need more tricks up your sleeve.
Oh, absolutely. Just plain B&B can still be too slow for large problems. You need ways to speed it up. And a major way is by adding cutting planes.
Cutting planes, like slicing off parts of the solution space.
Kind of, yeah. Think of them as extra constraints you add to the LP relaxation while the B&B is running. The crucial thing is, these cuts are carefully designed so they slice away regions of the continuous relaxation space that contain only fractional solutions. They never cut off any of the valid integer solutions.
Ah, so they make the relaxed shape tighter, closer to the actual integer points.
Exactly. They tighten the LP relaxation. A tighter relaxation gives you better bounds at each node in the B&B tree. And better bounds mean you can fathom more branches sooner. It accelerates the whole pruning process. The sources mention things like Gelmery cuts, MIR cuts. Apparently, MIR cuts are often very effective.
And how you actually write the model matters too, the formulation.
Immensely. This is huge. The way you translate your real-world problem into mathematical equations, the formulation can have a massive impact on how easy or hard it is for the solver.
How so?
Well, using techniques like disjunctive modeling, where you explicitly use binary variables to model either-or choices like either this set of constraints applies, OR, the set applies, can often lead to much stronger, tighter formulations.
Better than just using, what was it, big M?
Yeah, the big M method works, where you use a large constant M and a constraint like Y or M binary to turn something on or off. But choosing M well is critical. If M is way too big, it can make the LP relaxation very weak, giving poor bounds.
So smaller M is better?
A valid M that's as small as possible, yeah. But often, more sophisticated formulations, maybe using more variables or capturing the structure better, like the convex hull formulation, provide naturally tighter relaxations without needing big M tricks and help the solver much more. That facility location example showed how a disaggregated model was tighter.
And for those really enormous problems like the airline crew scheduling, even more specialized stuff.
Right. For problems with specific, very large structures like crew rostering or maybe cutting large rolls of paper into smaller customer orders, cutting stock, standard MILP might struggle with the sheer number of variables. So they use techniques like column generation.
Column generation?
Yeah, often within B&B, then this is called branch and price.
Right.
Instead of listing out all possible flight sequences for a crew, which could be billions, the algorithm cleverly generates only the promising sequences, the columns in the LP matrix, on the fly, as needed. Much more efficient for those types.
Wow. Okay, so there's a whole toolbox of techniques layered onto branch and bound.
Yeah.
Now, the outline hinted at something really cutting edge, machine learning getting involved with MILP. How does that work?
Yeah, this is a super active and exciting area right now. The motivation is simple. Even with all these clever tricks, some MILP problems are just fundamentally exponentially hard. So the idea is, can we use ML to make the solver's internal decisions smarter, faster?
So ML isn't solving the MILP, it's helping the solve the MILP.
Primarily, yes. Making better heuristic choices inside the branch and bound algorithm. For instance, remember the branching step, picking which fractional variable to branch on. ML models can be trained, maybe on data from past solves, to predict which variable choice is most likely to lead to good pruning later on.
Like giving the solver some intuition.
Kind of, yeah. Maybe mimicking what a computationally expensive analysis like strong branching would do, but much faster. Techniques like graph neural networks, GNNs, are being used here because the B&B tree has a graph structure.
Interesting. What else inside the solver?
ML can also help with node selection, deciding which unexplored node in the B&B tree to tackle next. And cutting plane selection, learning which types of cuts, or even which specific cuts out of potentially many candidates, are likely to be most effective at tightening the relaxation at the current node.
So making all those internal heuristic choices better using learned patterns.
Exactly. But ML and MILP interact in other ways, too. A really practical one is using ML for predictive analytics to generate better inputs for the MILP model itself.
Ah, okay. Like using ML to forecast demand.
Precisely. Or predict machine failures, or estimate travel times, or forecast energy prices. You use ML to get the best possible picture of the future, and then you feed those predictions into your MILP model to find the optimal plan based on that forecast.
So ML predicts, MILP optimizes based on the prediction, a hybrid approach.
Exactly. It creates these really powerful optimization learning workflows. There's also more futuristic research looking at things like end-to-end differentiable solvers or using reinforcement learning to train solver strategies, but that's still more on the research side. The main challenge is often getting enough relevant data for training, which people are tackling with online learning or transfer learning approaches.
It really does feel like those lines between traditional or optimization and AML-MEL are blurring. Before we wrap up, one last thing the outline mentioned briefly was MILP.
Ah, right. MINLP, mixed integer nonlinear programming.
So integer variables, like MILP, but now with nonlinear stuff too.
Exactly. Either the objective function or some of the constraints involve nonlinear relationships between the variables.
And I'm guessing that makes things even harder.
Generally, yes.
Yeah.
Nonlinearity adds another layer of complexity on top of the integer complexity. The blending example in the source hints at this. While you can model things nonlinearly with integers, you often want to avoid it if possible.
Why is that?
Well, for instance, if you have a term like a continuous variable C1 multiplied by a binary variable Y1, C1, Y1, that's nonlinear. Solving an MINLP with terms like that is usually much, much harder than if you can find a clever way to reformulate that same logic using only linear constraints, possibly introducing an extra variable to keep the problem in the MILP class.
So stick to linear whenever you can if you want an easier solve.
For integer problems, absolutely. Linearity is your friend when it comes to solvability.
Well, this has been quite the journey. We've really unpacked a complex but clearly super powerful field.
We definitely covered a lot of ground. We started with just defining mixed integer programming, that core idea of optimizing with both continuous and discrete integer or binary variables.
Right, understanding those components. Then we saw how essential it is in the real world, supply chains, manufacturing, services, even those complex industrial systems, finding exact optimal answers, driving real savings.
And we dug into how it works. That core branch and bound algorithm, relaxing, branching, using bounds from the LP, finding incumbents, and fathoming branches to prune the search.
Yeah, understanding that logic was key. And then all the enhancements, the cutting planes, tightening the relaxations, why good modeling really matters, and those specialized techniques like column generation for the massive problems.
And finally, we peeked at the cutting edge, how machine learning is starting to integrate, both helping the solvers internally and working alongside them in hybrid predictive prescriptive systems.
MILP really does seem like a fundamental building block for smart decision-making in our complex world.
It really is. It gives you that rigorous framework to turn these messy operational puzzles into structured math problems you can actually solve for the best outcome.
So for you listening, maybe a final thought to chew on. We've seen how MILP combines discrete choices and continuous flows, and how algorithms and now even ML tackle this complexity. As the problems we face get even bigger, more interconnected, and as AI techniques get more sophisticated, how might these optimization tools evolve further? Could we see future systems that can automatically formulate and solve problems that seem completely intractable today, really changing how we approach designing and running complex operations?
It's definitely a field that keeps pushing boundaries. Exciting times ahead.